Welcome to Chapter 5, Eigenvalues and Eigenvectors. And that is also the section title for 5.1. In this section, we're going to take linear transformations, which we've talked about before, and we're going to break them down. And for this information, all the matrices will be square matrices. And the ideas of eigenvalues and eigenvectors, you'll see these concepts applied in more advanced mathematics courses and engineering, physics, chemistry, places like that. So there is a lot of real-life application involved in this topic. So, as mentioned, we'll be dealing with square matrices. So remember that a square matrix can be used to define a linear transformation. And remember the notation for linear transformations looks like this, from Rn to Rn. So basically, this is just moving vectors. So let's look at an example graphically. So we have A, matrix A, and vector U and vector V. So we want to consider the products AU and AV. Well, if I want to find AU, I'll take matrix A times vector U, and remember, we'll multiply the rows by the columns, and we end up with this. Okay, well, that's shown to you here. Same type of thing, if I want to find A times V, I'll take matrix A times vector V, multiply the rows by the columns, and I end up with vector 4, 2, which is demonstrated here. Notice that AV is a multiple of vector V. However, U is not a multiple of AU. And this is something that we are going to look at involving eigenvectors and eigenvalues. So this is the same thing that we will be seeing in these future slides, just different notation or terminology. Okay, so for each matrix, there are special vectors with property such that AX equals lambda X for some scalar lambda. So just a Greek letter. So all it's saying is there is some multiple, some scalar multiple that makes this equivalent. So here's the new terminology. An eigenvector of a square matrix is a non-zero vector such that AX is equal to lambda X for some scalar lambda. Okay, so that's basically what we just said. The scalar lambda is called an eigenvalue of A. And that will take place if there is a non-trivial solution for this equation. Okay, so eigenvector and eigenvalue. So this part here, you can pause this and kind of take a look at this, but what we are seeing is that basically, if we have some vector that has a scalar multiple that equals the given vector A, then it is in fact an eigenvalue. Okay, so you can look at this if you want. But let's see what I mean here. So I have a matrix A and vectors U and V, and we want to know if vectors U and V are eigenvectors of A. So what we'll do, the first thing we'll do is we'll check U. So we're going to take A times U, just like we did previously. And when we multiply this, we end up with negative 24 and 20. Okay, well, it looks to me like these have a number in common. In fact, they have a 4 or even a negative 4 in common. If I take out that negative 4, I am left with vector u. So I can see that negative 4 times vector u is equal to a times u. So u is an eigenvector of A. And the eigenvalue would be negative 4. Let's check the other one. So now let's find AV. So I'm going to take vector A, multiply it by, matrix A, multiply it by vector V. And when I do, I get the vector negative 9, 11. Well, I want to see if this compares in any way to vector V. And it doesn't. There is no lambda that I can multiply by vector V that gives us this vector here. So this tells me that vector V is not an eigenvector of A because this is not a multiple of vector V. Not so bad, right? Okay, well, now we're going to take this a little bit further. The scalar lambda is an eigenvalue of A if and only if the equation, this here, has a non-trivial solution. Okay, so these are things that we've seen before. This is just a fancy matrix, so if AX equals 0 has a non-trivial solution, right? Okay, so if we want to show that lambda equals 5 is an eigenvalue for A, well, what we want to do is we want to start off with this equation. So we want to show that A minus 5I times X is equal to 0. Okay, so let's go ahead and first start with A minus 5I. Now, remember, I is the identity vector, or identity matrix, rather. So it's ones at a diagonal and zeros everywhere else. So matrix A is given to us here, minus 5 times the identity matrix. So just multiplying this, I'm subtracting this matrix. Okay, so we just subtract the corresponding entries, and we end up with negative 4, 2, 2, and negative 1. Okay. Now, again, I want to make sure that this equation here has a non-trivial solution. If it does, then lambda equals 5 is an eigenvalue. Okay, so what I want to do is I want to reduce this. This is row equivalent to this matrix. So just row reducing, right? Well, this row of zeros here, this tells us that the corresponding homogeneous system has a non-trivial solution. So this tells me that lambda equals 5 is an eigenvalue of matrix A. Okay, now in your homework, this type of problem will go on to say find the eigenvector or find n eigenvector or something like that. So if you go on and find the general solution, the general solution will give you that eigenvector. Okay, so just know that for your homework. Why don't you go ahead and pause this and try to answer this question. So this problem is the same as the one we just did. So what we want to do is show that this equation here has a non-trivial solution. And if there is a non-trivial solution, then yes, lambda equals 7 is an eigenvalue. Okay, so to solve this, a minus 7i, we'll set that up here. And 7i is just 7007. It's just 7 times that identity matrix. So subtracting corresponding entries, I get the following matrix. All right, so now what I want to do is I want to row reduce this. And when I row reduce this, I end up with this. And if you want to, divide by a -1 in that top row, that's just fine. But we can stop because we see that we have this row of zeros. This row of zeros tells us that we have a non-trivial solution. So that tells us that lambda equals 7 is an eigenvalue. Of matrix A. Okay, so here's some more information that we will find helpful as we move forward. The set of all solutions to this equation is the null space. Okay, so that, you should have kind of picked up on that a little bit. This subspace is called the eigenspace. And then the basis for the eigenspace is the basis for the null space of this. Okay, so the next example, I'm going to illustrate this last point here. Okay, so again, remember that all of these are going to be square matrices. So we have matrix A, and it's telling us that an eigenvalue of A is 2. And we want to find the basis for the corresponding eigenspace. I think eigenvalue, eigenspace, eigenvector, I think that's kind of fun to say. So make sure you try saying that out loud from time to time and see if you have fun with it too. Okay, so we are going to begin with A minus 2i because lambda in our case here, lambda is 2. Okay, so A minus 2i. All right, here is A. And 2 times I gives us this matrix here. And when we subtract the corresponding entries, we get the following. What do you know? That's interesting. Okay, so from the previous slide, what we want to do is we want to find the null space of this. Okay, so what we're going to do is we are going to row reduce this. All right, and when we row reduce this, since these are the same, it becomes this. Okay, that's fancy. All right, so if I'm finding the null space, what I need to do now is find the general solution of this. And we've done this lots and lots. So, you can go ahead and divide by 2 if you want. I think that you might prefer that. So if you prefer that reduction, that's fine. Okay, so our general solution will say x1 is equal to 1/2 x2 minus x3, and x2 is free, and x3 is also free. Okay, so this here will tell me what the basis for the eigenspace is. So the basis for the eigenspace is not that symbol, this. Okay, so values for x squared would be 1/2, 1, and 0. And then for x3, -3, 0, and 1. If you do not like that fraction, that's fine. You can let x2 be 2, and then you would have 1, 2, 0 instead. Okay. Moving on. So in general, we cannot find the eigenvalues of a matrix just by looking at a matrix. However, the eigenvalues of a triangular matrix are the entries on the main diagonal. So remember, if we have a triangular matrix, then we can easily identify the eigenvalues. So this last example here is directly from your text. Since we do have these triangle matrices, the eigenvalues for A are 3, 0, and 2, and the eigenvalues for B are 4, 1, and 4, so 4 and 1. So in the next section, we'll discuss a method for finding eigenvalues of a matrix. But the last thing I want to share with you is Theorem 2, which basically says if you have a set of eigenvectors that correspond to a set of eigenvalues in a square matrix, then that set of eigenvectors is linearly independent. And then the last thing, a matrix is considered singular if and only if 0 is the eigenvalue of the matrix. I think you'll find that this section and this homework is a bit of a relief and a breath of fresh air, if you will. Enjoy!